We can also look at one more example, which is for the design of corbel using strut-and-tie model. Now, what is a corbel? You can see that this is a corbel, and typically it is used in precast members. We are designing a corbel using strut-and-tie model, projecting a column of dimensions 400 by 400, and the corbel is subjected to a vertical load of 250 kilonewton and a horizontal load of 50 kilonewton. You can see, right. Now, cylinder strength is 40 megapascal and yield strength is 500 megapascal, right. Now, again, as we have discussed, the first step before we use a strut-and-tie model is to orient how the struts and ties are going to be formed, right. So, here you know that just like in your steel trusses, the loads are assumed to be applied on the nodes, right, or on the joints, right. So, here instead of joints we call them as nodes, right, and you can see here. So, this is so now that I have a compression load that it is coming, so that has to be somewhat transferred like this as a strut. So, these are all struts, okay, and it has to go vertical direction. So, this is your force. So, this is very clear. We also seen in the elastic stress analysis like that, right. Now, I need to balance this. I need to have tie connecting here, right, and this is what it says. So, this is going to be tension, this is going to be compression, and these are all compression element, and the red colors are all tension element, right. So, we see. So, this way we can form. So, the loads are assumed to be acting on these locations, right. Now, construction again. So, we have formed this kind of a strut which is efficient configuration, right, and let us look at it now. How do we find? First, we can find the compressive force in this strut, vertical strut at location D, FD if we call it, and let us assume that this is going to have a width of half A. Again, width of the strut I am taking it as A. So, I am saying from the edge it is going to be at a distance of half A. Now, when you take moment about this point, right, you can see here it has to be 250 kilonewton. Now, what are the distance you can see here? 250 kilonewton is at a distance of from here to here, which is 350 plus this 120, right. So, 250, 350 plus 120 is your lever arm, and that is producing a clockwise moment like this, right. And then 50, now I am again taking a moment about this point. So, what are the distance? It is going to be, for example, see I said that this force, everything is assumed to be acting like this, right. So, we are taking distance from here to here. So, you can see here it's basically assumed to be 470, which is this distance, right. So, you can see this is 470, right. So, from here, right. So, here we are assuming, so half VA is equal to 30 millimeter. So, you can see here that is why I am subtracting from 500 this 30 to work out to be 470, right. Now, 50 is kilonewton multiplied to Newton by 1000, and then I am lever arm is this. So, this is again producing a clockwise movement. Now, you can see that FD is going to be anti-clockwise movement. So, that is why I am putting it on this side. So, you sum them up. So, it is going to be FD multiplied by this distance, which is basically you can see which is 350 minus half of A, right. So, that is what you get. So, you substitute that and then you get value for FD in the in terms of A, okay. So, if you substitute that in terms of, so FD I found out in terms of A, because A is what we are trying to find out what would be the width of the strut. So, we have found force in terms of that strut. So, if you substitute now the stress in we can also invoke another condition. The stress in the nodal zone at that point D is typically limited to 0.75 times the strength reduction factor times F prime C, right. So, now you can see 0.75 times strength reduction factor is taken as 0.7. Now, compressive strength is given as 40 and the width of that corbel is 400, and let's say that it is going to have a dimension of A. That's what we are trying to find out, the width of the strut A. So, FD is basically 8400 into A. These are the two conditions that we are trying. First, we are taking the moment about point A, because the external moment should be equal to your internal moment. That condition we are applying. The second condition is this force FD is passing through this node, that again the node also has a limited capacity in taking that force, right. So, using that again we are finding a relationship between A and FD. So, now that I have two conditions, so you can calculate, and A works out to be 51.8 millimeter and FD is 435.1 kilonewton, right. So, again here this 30 mm we are taking it from cover point of view, right. So, we are assuming that the tension tie minimum it will be put at a distance of 30 mm. Now, what are the members CD? If you look at the member CD, you can see this distance, okay, we are trying to calculate from here. So, this is your horizontal projection, which works out to be 120 plus this distance, which is basically this distance is nothing but 0.5 times A, which is basically your 51.8. So, that works out to be this plus this, right. This is 120, this is half of A. So, half of A plus 120 is 146 millimeter, right. Similarly, member BD, when you look at it, this distance is going to be basically 350 minus half of 51.8, which is 324 millimeter. So, this distance is 324 millimeter. Now, we have found out what is A and what are the forces. Now, let us look at the forces in the truss by statics. Okay. Now, how do we do that? Okay. For example, I can I can take these things in a clever way. The compressive force in the strut CD and tension tie BC can be found by taking equilibrium on the joint C. So, let us look at now joint C. I have a compressive strut, which is this FCD, and then I have externally, again I am just like your truss analysis in steel, we are going to transfer the forces to act on these nodes. So, that is the reason these forces are transferred to act on the force, which is 50 kilonewton to 50 kilonewton. These are external, and then you have a strut that is coming FCD, and then tension tie that is going FBC. This, of course, this node joint has to be in equilibrium. So, we take from equilibrium direction. So, basically we can calculate this theta, right. So, this theta can be calculated, which is basically, what is this, how do you calculate this theta? So, basically, right, this is your 470 and this is 146. So, theta is going to be 470 by 146, and you take tan inverse, the angle is again 72.74, which is greater than 25 degree, right. And then you take vertical force equilibrium. So, FCD sin theta should be equal to 250 kilonewton. So, your FCD works out to be 261.8 kilonewton. Then you take horizontal for equilibrium, then FBC has to be equal to FCD cos theta plus 50, then FBC works out to be 127.7 kilonewton. So, now in this, using the joint, we found out what are the compressive strut force in CD and what are the tension force in CB, right, force FBC. So, we found out, right. Again, what we can do is we can, now we have found this and we have found this. Now, I need to find out what is this and what is this. Okay. Similarly, what is this, right. So, by taking joint equilibrium at D, now again we can look at it, what are the forces that it is coming, FPD and FPCD, already we have calculated that, FD we already calculated that, FAD and FPD I do not know, right. So, we can use the equilibrium condition. Now, what is alpha and beta? This is purely a geometry. So, alpha you can see here, it is from here to here, right. So, this is basically your alpha and this is your beta, right. So, you can say alpha is tan inverse of 324 by 470 and beta is tan inverse of 146 by 470. You get 17 and 34.58. Then simple statics, you can take vertical force equilibrium, FBD cos alpha plus FCD cos beta is equal to Ft that you have. That what is this on this force? We already calculated that as 435.1. So you can get FBD as 224.8 kilonewton. Now again invoke your horizontal equilibrium and I can find out FAD, which is a tension tie, force as 49.9 kilonewton. So now we have found out this, also we have found out, now we got all the forces that what we wanted, right. So we can go back and okay. So there's one more thing that we have to find out. We have to now find the members. We can cleverly do by using the method of section. So you must have studied in your basic engineering mechanics course. So you can take a cut which is cutting through the members to expose your internal forces. Then you can use your statics to find out the unknown forces, right. So you can take a horizontal section like this XX, which is going to cut AB, BD and CD. Now we can find out BD and CD we already know, only thing we don't know is AB. So we can find out like this. So FBD is known, FCD is known, FAB I don't know. So you can equate this angle gamma is 470 by 324, which is 55.42. So we can again find out your vertical equilibrium, FBD times 324 plus 146, right, minus FBD sin, basically I am taking moment about moment equilibrium about point C. So about this point I am taking. Anyway, this is going like this, so there is no problem, and this is a vertical component I take, and FAB, this distance is 324 plus 146, and this is creating a counterclockwise moment, and this is creating a, right. So this is creating a opposite. So basically counterclockwise moment. So it is creating like this. So that's the reason. Okay. So this is let's say this is positive mean, this is going to be negative, and we take that to be 0, and then you find your force FAB, and FAB as 185.1 kilonewton. So you expose the internal forces and you take moment about any point in such a way that you reduce as many unknown quantities as possible, because FCD is going through C. So I need to deal only in terms of FAB and FPD. So using that simple method of section, now we found out what the force in the tension tie AB as well. So we got all the forces, right. So and now let's look at it. AB is a tension force. We can see this is a tension member, tie member, and BC again tension, right. CD compression, strut, and BD again compression, right. AD again which is tension, and these are the forces. So these are the struts and ties forces that we have calculated. Now we need to again check the capacity of the ties and find the reinforcement and find out whether the struts are having adequate capacity or not. Okay, let's look at it. Now we are going to design the tension element. Now let's look at again. Now that we found out all the forces, let's look at the first tie, which is FBC. The area of steel that is required will be force divided by 0.87 times Fi. So you can quickly run your numbers and you get your area of steel as 293.3 millimeter square. So we can provide 4 numbers of 12 mm diameter bars. So it's always when you do it, you select a smaller bar diameter, and so that you have nice distribution of steel within the tie region, right. It's always not a good idea to put one big bar, rather you select small diameter bar. At the same time, you should choose in such a way that you can also concrete that area. If the spacing becomes too tight, then the aggregate cannot get in and you will have some segregation and other issues that we need to be careful. But without violating the concreting difficulty, we should always use low diameter bars, right. Now the area of reinforcement required for tension tie AD, now if you look at it again, go to the same force we found 49.9 kilonewton, that you divide by 0.87 into Fi, you get area of 114.71 millimeter square. So, we can provide two numbers of 12 mm bar, so which is 226. So, regarding the tension tie AB, this is very important because this is a part of a column, right. So, column member will be subjected to compression as well as bending, right. So, a reinforcement will be, the requirement for a column will be governed by the both the amount of mostly from bending moment, that what is acting the cross section. So, we have to see. So, the tension tie whatever the AB that we have, we need to provide in addition to what you have for the design of a column member, right. So, this tension tie AB, the longitudinal reinforcement will be designed to resist this force. In addition, we also want to continue the 4 numbers of 12 mm bars sufficient distance down to the column, right. So, more than where the tie is forming. So, this is in extra. So, whatever that AB member reinforcement is there, that should be extra to column longitudinal bars. Okay. Right. Now that we found out the amount of tension tie reinforcement, let us look at now the design of nodal zones. Okay, what are the nodal zones? For example, the width A that is designed at a nodal zone was calculated based on nodal zone stress limit. It's because the width itself what we found was from the stress limit requirement. So, the verification is not really required. So, we found out only from that stress limit. The dimension of A itself was found out using the stress limit. Now, to satisfy the nodal zone stress limit now at C, when you look at it at C, we have to again check. So, the tension tie actually whatever that you are providing must engage an effective anchor length in the concrete at least equal to, that is what we are trying to find out. FBC we calculated to be 127.6, right. FBC is again tension tie member. At that nodal region, we are assuming again 0.75 times the strength reduction factor times F prime C. Then the diameter of the size of the width of the column, which is 400. If you see that the dimension that it is required is 15.19 millimeter, right. So, the tension tie must engage an effective, it should have adequate anchor length, right. This bar BC whatever that we are providing here, it should have adequate anchor length so that it is not going to come out easily, right. So, we have to provide a 15, this requirement is only 15.19, but we are going to provide a 50 mm depth L shaped bend bars in as a BC member, right. So, that is one thing. So, now we have checked everything, we have to check now compressive stress, compressive strut, right. So, tension tie we have checked, nodal stress limits also we checked. So, let us look at now compressive stress struts. Okay, just like we did for the post tension beam, here also you look at it, first you look at the compressive strut CD. Now, at joint C, if you look at it, the width of the bearing plate is 100 millimeter, right, and the width of the tension tie that we worked out was about 50 millimeter, right. So, this is your bearing plate dimension which is 100 millimeter and the tension tie we worked out to be 50 millimeter, right. Now, I am calculating what are the strut, this width we are calculating. Now, this width is summation of this plus this, right. Now, both of them if you look at it from simple geometry, the moment you calculate your theta, the WCD is nothing but width of the bearing plate times sin theta and then the width of your tension tie multiplied by cos theta. So, using a simple geometry, in the last lecture itself we have shown how this is coming from simple trigonometry relationship. So, you can find out the width of the strut using this expression. Now, the theta angle from geometry we previously calculated to be 72.7 degree. So, width of the strut, then if you plug in the numbers it works out to be 110.35 millimeter. Now, joint C, again the allowable stress we are taking it as 0.75 times strength reduction factor multiplied by F from C. Strength reduction factor I am taking 0.7. So, that is about 21 megapascal. So, I can go back and put the allowable stress multiplied by the area of strut. Now, area of the strut, the only thing that we did not know was the width of the strut. Now that we have calculated, the area of the strut will be 110.35, which is the width multiplied by the thickness of the member on which it is acting, which is 400, right. So, if you substitute, you get 926.9 kilonewton, which is far greater than what the compressive strut it was have to be. It is only 261.8 kilonewton we got from your force analysis. So, the capacity of this strut is higher than your demand, right. So, so this is also okay. And now again we are checking for the compressive strut B. Now we check this, now we have to check this. How about compressive strut BD? Again using geometry, resisting the tension tie, the width of, assuming that same as the tension tie width as BC, we take 50 mm, same thing that we are taking here. So, if you take that here at joint B, when you look at it, the width of the compression strut will be equal to this side also I have 50 mm, right. So, if you take both of them, the width of this strut is going to be 50 times sin gamma plus 50 times cos gamma, and gamma from geometry works out to be 55.4 degree, that we have already calculated that, right. So, this is your 55.4 degree, right. So, if you substitute that, you get the width of the strut BD as 69.55 millimeter. Now, you see here I have in this joint the allowable stress I am taking it as 0.6 times strength reduction factor multiplied by F prime C, right. Now, why do I take 0.6? Now, you see here in the joint B, I have a tie here and a tie here. So, in a joint, if I have two ties that are coming, then the allowable compressive stress I take it as 0.6 times strength reduction factor, which is again taken as 0.7 and multiplied by 40, which works out to be 16.8 megapascal. Again, I substitute this stress, right, I mean 16.6 times strength reduction factor F prime C multiply area of strut is 69.55 is width, and perpendicular to the plane where we are looking at it, the width of the column is 400. So, you multiply that, that is 467.4 kilonewton, which is higher than 224.8 kilonewton. So, therefore, it is okay. So, that means this strut BD is also okay capacity wise, this we have checked, right. So, now we have to go and check for minimum reinforcement requirement. So, again as the code says, ACA 318 gives you much more elaborate requirements. So, that is the reason we are using ACA 318 provisions. The amount of tension steel minimum should be 0.04 times F prime C by F5 times PD, right. So, if you substitute that, that works out to be 601 millimeter square, which is greater than what we have provided. For example, for tie BC, we calculated 452.4. So, the minimum requirement is higher than that. So, we have to increase the tension tie to 6 numbers of 12 mm bar. Initially, we calculated 4 numbers, right, of 12 mm bar. Now, I have to increase it to 6 numbers of 12 mm diameter bar, right. Now, so the provided tension tie is 678.6, which is greater than 600. So, hence it is safe. So, we have, so here you see here for this tie, the minimum reinforcement is governing, not the reinforcement you calculated from the tension force, but actually it is the minimum reinforcement that it is actually governing the design. And now, we have to again check for the minimum reinforcement requirement. So, as per ACA 318, this is we have to is a very careful. Corbels with shear span to depth ratio less than 2, they also need to satisfy one more important requirement. That means, we need to provide closed stirrups parallel to the primary tension reinforcement to prevent a premature diagonal tension failure of the corbel. Okay. Code also wants, when your ABD ratio is less than 2, in addition to your tension tie, we should also have closed stirrups which are parallel to the tension steel. So, that steel is basically distribution of that steel is required in accordance with ACA 318, 2/3 of the effective depth closest to the tension tie where you are providing. So, let us check. Now, the Y that is in the red color, what we are seeing, these three are your AH requirement, minimum requirement. Why? Now, you see here there is a crack that it is going like this, right. So, if it is cracking like this, right, then it should not fail in a diagonal tension failure. So, you need to have minimum reinforcement that should cut that crack and arrest that crack, so that it is not going to fail in a premature failure. Okay. So, that's what we are saying. So, that tension tie whatever that we have is actually is arresting this flexural crack, but there is also a chance that it may fail like this in a diagonal tension. So, the code wants you to put some additional steel. So, what is that additional steel? Now, if you do not have this AH, the cracks width may significantly widen, and you know the diagonal shear crack, it can propagate very quickly, it can lead to brittle failure. We do not want that, right. So, the code wants you to provide this additional reinforcement as a function of half of AS minus AN. What is AS and AN? AS is for the top tie and this is for the bottom tie. So, whatever the difference is there, that you take half of that and you distribute it over the distance of 2/3 of D, right. That is what the code is saying, 2/3 of your effective depth. So, let us look at it now. So, AS and AN are tie reinforcement in ties BC and AD in this example. So, if you calculate that AH works out to be 563.9 millimeter square. So, we are saying okay, for this I can provide 6 numbers of 12 mm diameter bar as a closed stirrup. See, note that point, it should be a closed stirrup which is going to confine and not let that crack to open up very quickly. So, this is again detailing requirement. So, you know in reinforced concrete and pre-stressed concrete, detailing is very important. Otherwise, though you may assume struts and ties forming, but if the reinforcement is not properly placed, it may lead to some cracking and then premature failure. So, we need to be careful. Okay. Now, finally, let us look at the detailing of the corbel. We have looked at the design. So, we are providing again extra stirrups again here, and then this red color is also extra stirrup. This is what we said, 6 numbers of 12 mm diameter hoop reinforcement, and we found main tie reinforcement at 6 numbers of 12 mm dia as a main tie reinforcement, and this is when I take the section at AA. I mean, I should say this as AA, right. So, column reinforcement here I am not really showing for clarity, but in addition to that you also will have column reinforcement that it will be going, right. So, this is the way we designed the corbel using simple strut and tie model and with some simple design guidelines that we have discussed it in the initial part of the video. Okay. So, let us summarize what we have discussed today. We have explained clearly the step-by-step procedure and guidelines for how to formulate an efficient strut and tie model, and we discussed very important example of design of a post-tension deep beam. We also discussed when do you call the beam as a deep beam, right. We looked at what are the significance of A/D ratio and L/H ratios, and then finally we also discussed one design of a corbel using strut and tie model, right. So, with that we are completing this strut and tie model. Now, in the next lecture we will talk about connections issues in pre-stressed precast members. Thank you.